Okay, so just a couple of quick things. So the homework solutions are available on Canvas for homework B1. There's a new ICA. Homework C2 is available. It's due in about 1 week. So it's basically due on the day of lecture D2. So that's about a week from today. You may have to do a little bit of book reading, but I've given some examples online, and it's pretty light. The kind of the reading ahead. I just wanted to make sure I got enough practice in before the midterm, and so that required kind of needing to get C2 out and back so that we could get the homework D out, so that we had that. And again, enough of that practice before the midterm coming up. So again, you may have to do a little bit of book reading, but it's very formulaic. It's just kind of, looking up the formulas for these particular random number generators and then plugging in and applying those. So that's what I mean. Like that content's covered in lectures E1 and E2, but that's technically, after the homework is due. But you can either look ahead to those lectures, which are available online, or just again look at the book. It's that part of the homework is relatively straightforward. Again, it's just plugging in. Okay, so just as a reminder, end of September, if you're interested in the Rockwell arena competition, that's when the registration's due. Similarly, toward the end of September is the FlexSim competition, and I think similar deadlines for Simio. So, questions? Okay. So we have been starting to talk about discrete event system simulation. That's what we're building up to. We've been doing hand simulations of that, both in lab and in class, but then we've been hinting at these other simulation frameworks. And so in lab 3, you've started working with Monte Carlo simulation a little bit. And I've mentioned, there's agent-based modeling and there is the system dynamics modeling. And so, the appeal of simulation in general, there's this simulated worlds article that I've got posted online where they're sort of talking about how discrete event system simulation models are really well suited for a wide range of different application areas: parts, patients, vehicles, manufacturing, healthcare, services, logistics, transportation, military operations, just to name a few. And this article links to a wide variety of DES simulation packages, including things like FlexSim. So, I've talked about Arena is what we'll use in this class. FlexSim is a competing product. Simio is another competing product. So this is meant to kind of support that these simulation methodologies have wide applicability and are only growing in their use as systems become more and more complex and requiring more empirical support before you go and actually build the system. But there are other useful simulation frameworks that we've been kind of hinting at. And so this week, we're kind of introducing agent-based modeling, system dynamics modeling, and then you'll have an opportunity in Lab 4 to work with agent-based modeling. And then starting in the Lab 5, beginning in next week, that's when we start just basically committing to discrete event system simulation for the rest of the semester and using Arena as our tool for implementing those models. So, as a reminder, I've kind of mentioned this before. I introduced these modeling frameworks. ABM, or individual-based modeling, is kind of the most realistic detail and scaling. You're modeling individuals and their agency, so you don't know the events ahead of time. You just kind of got to let time progress in very small steps and then ask all of the agents in your entire simulation world, what do you want to do right now? And then that logic comes from the agents themselves, and that it generates changes in the system. So it's very microscopic. It's like simulating every molecule of air in the room. Whereas if we contrast that with system dynamics modeling, this is a smoother version. It's like more like modeling, instead of modeling every molecule in the room, it's like modeling the pressure in the room. And so you're aggregating over lots and lots of individuals to get one single number or a couple of single numbers which capture coarse-grained features of the system. So you've got coarse-grained features on this side. So they're the lower resolution, so high transferable insight, metaphorical. So they don't quite give you the minute by minute, second by second variations in the system, but they give you kind of average behavior that you can have over long time periods. And then what we've been talking about, this process-centric discrete event system simulation, which tries to strike a balance between those two, where we still have individuals being modeled in the system, but the logic is coming from the process side. So it's easier to model, it's quicker to simulate. We don't quite get as many crazy corner cases that can occur with agent-based modeling, but we do get quite a lot of diversity in our outcomes. And so again, hopefully it's sort of this nice illustrative level where we're balancing between having so much realism that our sims take a very long time to run and are just as hard to understand as the real system, and so little realism that although we get some general principles, those general principles, like all of the systems that we actually want to do application in as engineers, become special cases where we have to perturb off those general principles anyway. So that's kind of where this discrete event system simulation is. But before we can kind of appreciate that, then it's nice to kind of know a little bit more about these alternative modeling forms, which you do use in some cases. It just kind of depends on what questions you're asking. So I mentioned system dynamics modeling, the coarsest grain example of modeling. So you usually use these with stock and flow models. And so you draw, usually system dynamics modeling tools are still graphical tools like Arena, where you are drawing diagrams. But the diagrams you're drawing look like this, where you've got boxes representing state variables that could change over time. And those boxes are connected to these thick arrows with these valve symbols in between, which represent flows. And behind the scenes, so you can drill down into flows and you can set up expressions which represent, based on the other state variables in the system, what is the rate of change of that stock. And you can drill down into the stock and you can say, what is the initial condition of that stock? So this should look like an initial condition problem. So in fact, this diagram here is represented by this differential equation here. So behind the scenes, when you draw this diagram in a system dynamics modeling tool and you set up an initial condition here and an expression there, behind the scenes, it basically writes out a differential equation for every one of the stock variables in your system. And it basically sets up a system of these differential equations. And then it numerically integrates them instead of integrating them by hand like you do in a calculus course. And then from there, it generates time series, which are consistent with these differential equations. So this is really just kind of a graphical front end to writing complex differential equations that are so complex that there's no use in analytically trying to solve them like on paper. So we numerically solve them instead. And so we've seen, some examples of that when I introduced the course. So this is kind of a popular system dynamics model for understanding epidemic spread through a population. So you have 3 state variables: the number of susceptible people in the population, the number of infectious people in the population, and the number of recovered people in the population. And so sometimes people say infected, technically, so I put it in as infected here because that often comes up, but the key point here is they're infectious. And so the rates of change here, if you kind of drill down into them and kind of think about it, they represent, if you had this many people in your population, what would be the general rate of change of those groups? And so we don't know where all of the susceptible people are. We don't know where all of the infectious people are. But we know there's some probability that a susceptible person is going to randomly bump into an infectious person. And if they randomly bump into each other, there's some probability that the infectious person is going to get the susceptible person sick. So we basically say how many susceptible people we have times how many infectious people do we have. And then we group all those probabilities together into a constant, a rate constant, and that represents the outflow of the susceptibles and the inflow to the infectious. So that's where that flow logic comes into play. That links to that. And then likewise, we know that the infectious individuals, after a certain amount of time, on average, are going to get better, and then they'll become recovered. So we can say, well, how many infectious people we have for each one of them, what's the rate at which they transition to being recovered? That's the outflow out of that stock. And then that outflow has to go somewhere. So it goes into the recovered stock. So the inflow of the recovered stock is the outflow of the infectious stock. And so again, you can see how this could be drawn as a stock and flow diagram and then translated into this form. And then you could just numerically integrate this equation to see what happens to susceptibles, infectious, and recovereds over time. And that's what people do with stock and flow. That doesn't say at any instant of time, like what are the what's the minimum number of infectious people I'll have? What's the maximum number? It doesn't capture those day-to-day variations. But if you were to average over all possible universes where this potential epidemic could happen, this would be the average behavior across those universes. So that's what we mean by system dynamics modeling. Right. So this is how that would look if you drew it in an SDM tool. So this is one, I think I drew this in VinSim, I think, or no, maybe I borrowed this because I think I would have put infectious here if I drew it. But you can see I've got three state variables, these stocks, susceptible, infected, recovered, and then those differential equations link them together. And then you draw all the causal links just to remind someone who's looking at the diagram what these rates depend on. And a lot of times you then annotate them with whether it's a positive causal relationship or a negative causal relationship. And the reason you do that is then very quickly you can see where you have positive feedback loops and negative feedback loops. And so system dynamics modelers are really big about looking for patterns of feedback loops, because then they can have theories of, well, when you have a bunch of feedback loops of particular polarities in particular orientations, generally the system behaves in a particular way, and generally we can intervene in certain ways. So some of system dynamics modeling is looking for those patterns and then using those patterns to suggest ways to intervene. So this is not something that we touch on in this class because we have a whole nother class based on exactly this. IEE 477. The tool they use there is AnyLogic, but there are a bunch of other tools like VinSim. Even in NetLogo, it has a system dynamics modeling tool built into it. So there's a bunch of SDM tools. It's a very popular modeling approach, especially for people who do strategic modeling, like in business. So that's system dynamics modeling. So sorry, I have to use a different clicker today. So now agent-based modeling on the flip side of that, that's what you'll actually be practicing with in the lab 4 that you're going into here. So in agent-based modeling, again, spatially explicit models typically, I've already seen some examples of this in the intro. So, in this particular predator-prey model, you actually are modeling all of the wolves, all of the sheep, and actually all of the grass. In the field, you model how quickly the grass regrows. That affects the regrowth of the sheep. How many sheep they are affects the regrowth of the wolves. And because of all of those individual dynamics at the population level, you get a lot of variation out. You get a lot of squiggly lines here. So you capture a lot more realistic variation. But you can imagine that, I'm only simulating less than 100 sheep, but so like 100 sheep and 153 wolves here. So if you wanted to scale this up to actually, simulate a real model, like a real world, like an actual expanse of space equal to, a national park or something like that, then not only would this have to be much larger with maybe more predators and more prey, but you would actually have to then couple in all sorts of interesting details about the landscape. And there is an extension of agent-based modeling called ABM GIS, where it uses geographic information systems, another very popular framework in data science, where people do that. They try to scale the agent-based models up, and then they put the features of maps right onto it, like real features of maps, and then see how people behave. And so I think I've got an example of that, if not in this one, I think I've got in the pre-lab, I've got an example of that where people did that with Florida. So I actually wanted to see, based on how we get information to people in Florida as hurricanes arrive, what is the most effective way to balance our portfolio of emergency distribution of information so that we can actually maximize how people get out of Florida, keeping in mind that there will be bottlenecks as people come to the highways. So we need to somehow get people to leave early, but we don't want to give them too much information early that makes them, if there isn't a hurricane, not listen to that information in later hurricanes. And so they're trying to balance all of that behavior all at once on top of a real map. So you can imagine that that would take a lot of computing power, and you're not going to be able to run a lot of replications of that. So that's kind of the downside of using these agent-based models, is that they have the potential to be overly complex. And so sometimes the best use of these is to sort of look for general principles that are too difficult to model mathematically, but that you don't put quite enough detail in to make it a special case where it only applies to, let's say, Florida. So those are some of the examples that I'm going to have you do in lab 4. I got sort of 2 examples that there's enough complexity that it would be difficult to figure out what the math, but it is sort of simple enough that it can generalize to a wide range of systems. So a lot of people use agent-based modeling. So in biology, they often refer to it as IBM, or individual-based modeling. So they model things like fish schools, bird flocks, complex ecosystem interactions. In the social system sciences, that's kind of where agent-based modeling got its popularity at first. They model everything from ancient civilization. So, you know, there are people here at ASU who try to understand why artifacts show up in the ground in different spaces. And they use agent-based modeling to sort of kind of do hypothetical, you know, it's just, they test hypotheses about societal interactions that were long ago that could generate different distributions of artifacts and see if they match the distributions we see now, and use that as evidence of whether this particular society did things one way or another. And that's an example of what they use agent-based modeling for. Of course, you can model modern societies as well, organizations, stock markets. And then there's something that goes beyond the scope of what you'll do in lab 4, participatory simulations, where you actually can not only have kind of non-player characters running around like usual, but you also have real humans who take the role of individual characters in the ABM, and you can see how they interact with each other in your artificial environments, as well as these kind of, again, non-player characters that are kind of running around them. So it becomes more like a game, but it's sort of an experimental game and to learn about these interactions. So engineers that use ABM often use tools from a related field called multi-agent systems, where the goal there is less about generating a lot of empirical data, but more about having a test bed to test ideas in small numbers of replications just to see if it has face validity before you go and build the real thing. So these 3 terms get thrown around a lot. They're very, very related. Sometimes the software packages overlap between them: IBM, ABM, and MAS. So if you hear any of these, it's totally reasonable to just sort of swap one for the other in your head, because there's there's really no difference between these 2 aside from the name, and there's only nuanced differences between MAS, and it's really just, you know, the people who use MAS are often, you know, not trying to make inferences; they're sort of trying to do testing, and that's kind of the slight difference there. But for a lot of operations research and IE that we're using, like that we use them more like the social scientists. Then here, the MAS is like more like mechanical engineering use here. So I want to build 15 robots. I think this algorithm will work. I'm going to test it in a multi-agent system, see how it works there, adjust a couple of parameters, maybe do some optimization, and then implement it on 15 real robots. As opposed to here, where it's like, what would possibly happen if I put a bunch of people and a bunch of machines in this novel environment? There's a bunch of possible things that could happen, and I'm not quite sure. So I'm going to create a simulated mixture of these people and technology together and see the different outcomes that come out of that, and then use that to inform my decision making about what designs I should do. So MAS are often design first, test in MAS. ABM is often design later. So you learn from the ABM and then you do your design or your intervention. But again, those are nuanced differences. A lot of different platforms for agent-based modeling. you'll get exposed to NetLogo in Lab 4. It's just an easy one to start with, but there's programs, there's things based on Java and Eclipse like Repast and Relogo. There are toolkits built within Python, although PyABM isn't quite maintained as well as it used to. There are specialized commercial programs like Altriva that big commercial companies will buy, and they've got all sorts of fun features. And then there are highly capable commercial programs that are used more widely in the industry, like AnyLogic. And this is actually a multi-sim program. It does DES, ABM, and SDM all in one package there. So it's also very popular. So a lot of different ways to do agent-based modeling. So you'll see in Lab 4 that we use a slightly different lingo for talking about agent-based modeling. We talk about agents instead of entities, but the agents really are the entities in the agent-based modeling. Our time can jump in a variety of different ways. So because we don't have an event calendar, then you typically move time ahead in regular jumps, but you don't have to. So you basically just jump ahead to certain times, and then again, ask the agents based on what is currently going on, where all the other agents are at this time, what changes would you like to make to your state? And then you move on from there. So typically that's in regular jumps, but you could really do the sky's the limit. You have kind of total control over the timing of these things. You view the agents as parallel processes that are just running at the same time. So that becomes that adds a complexity, because how you implement parallelism can differ from agent-based modeling program to agent-based modeling program. So some programs might always iterate through the agents in the same order when they're updating their state variables. Other programs might go through them in a random order. This unfortunately means that sometimes your results might change if you re-implement them in a different software program. And it's important to understand the assumptions that the programmers made when they implemented that program. Microscale simulation, spatially explicit, fine-grained, can be very slow, but is very general purpose. And so that's ABM. So an example of how industrial engineers are using ABM more and more comes from this article that I put on Canvas, the pedagogy of zombies. So this is an example where this LMI, which is a not-for-profit strategic consulting firm that works for NASA, and in this case, we're interested in using ABM to model how commercial airlines respond to new policy scenarios. So they wanted to put planes up in the air and people down on the ground making decisions based on their local environment. And so wanted to see, like, is this going to lead to congestion? Like, if you change these policies and it slows these things down, are you going to tend to get more congestion, and so on and so forth? And so these are the types of things they would do, but then they would invite interns in, often from operations research and IE and management science. And those interns and co-op students didn't have agent-based modeling background from their coursework. And so they'd spend their whole summer just learning about agent-based modeling. And then by the end of the summer, or the end of their internship, then they didn't end up getting a whole lot done. And so what LMI ended up doing is that they created a kind of competition similar to the arena competitions I was talking about, that would encourage students to learn about ABMs back at their home institutions, so that when LMI would employ them, there was a greater chance that they would have some exposure and background, be able to hit the ground running. And so they kind of came up with a cute competition idea here. And so the idea was that in this competition, there would be a layout, a floor plan of a building, and you might not know that floor plan ahead of time. Your job was to build behaviors of humans that would move around in this floor plan and hide from an impending zombie apocalypse that would be released into the building. And so they had zombies that had a behavior that was known by the competition. They had a floor plan that was known by the competition. And then the students would then submit different sort of behavioral strategies, like find the first room you can and go into it. Or choose a room that only has one entrance or something like that. So you would have these humans that would scatter around and they would hide in different ways. And then for every student strategy, they would run the agent-based model through several replications. And they would say, over a day of having to go through this zombie apocalypse, how many of your humans survived? And they would then compete the different strategies against each other. And then you would get monetary prizes or and so on, similar to the Serena competitions based on if your hiding strategy ended up being the most effective. And so that was kind of the framing that they used. Again, that's why the article is the pedagogy of zombies, using this kind of zombie scenario. It's kind of a cute idea to get people into this agent-based modeling that they weren't necessarily getting in their curriculum. And so this was one of the reasons why I thought, I wanted to at least have one lab where you used to have some exposure to agent-based modeling, because there are industry partners out there employing IEs and ORs that are looking for it. And interestingly enough, I was teaching a short course on discrete event system simulation modeling at UNLV several years ago. And there's a grad student who was sort of acting as a TA for the shorts course. And he was doing agent-based he didn't know about this competition, but he was doing agent-based modeling for thinking about architecture and thinking about architecture of buildings in the face of potential active shootings. And in his approach was almost identical to this, to sort of think, how do we build architecture that guarantees that if you have a basic human model of how humans behave, you're now, instead of designing the behaviors of the humans, you're designing the space to sort of guarantee that there's more refuges for people to survive such a terrible event. So although this was kind of a cute framing of this setup, it turns out that it actually was very real, is that, in parallel with that, there were groups using agent-based models to study a very, very similar problem and almost kind of an identical test case there. So it's kind of an example of that. Other examples of ABM that, Southwest Airlines was one of the first to use ABM to talk about airport operations. And so there's a bunch of different, we've talked about optimizing, seating order, but there's other things like cargo management. So a lot of people don't realize it, but when you get into a commercial airline, or when you're flying just from point A to point B, there's a lot of cargo space that is not luggage. So there's just free space in there, but they never know exactly how much free space they're going to have ahead of time, because they don't know how many checked bags they're going to have. So kind of at some point, they sort of get an idea of how much space is left over, and then they rent that space out to logistics companies that need to get their stuff from point A to point B. Now, so stuff's just waiting to get on a plane. So then the question is, what plane do you put it on? Now, if you need to deliver something from Phoenix to Columbus, Ohio, then of course the obvious thing would be to wait for a plane that's going to Columbus and put your stuff on that plane. But there may not be that many planes going from Phoenix to Columbus. So an alternative approach might be just to put it on any plane and just see how long it takes to eventually get to Columbus. So if you happen to be at an airport where right then you have a flight that's going to Columbus, then put it on the plane to Columbus. Otherwise, put it on any plane. And so they tried a bunch of these different scenarios, and they just used an agent-based modeling to see how long did it take luggage to get from its origin to its destination. And they found that they could minimize delays by doing that second policy that I said there, where if there's no direct flight available, just get it into the air. Because if a plane is in the air, it will likely be going to a hub. And if it lands at a hub, there will likely be a flight to its destination or toward its destination. And so that was a much better use of the luggage time to wait in the air than to wait down on the ground. And that's something that they discovered by using agent-based modeling to test a bunch of these different strategies. So that's also how, I think I mentioned this before, they kind of discovered that boarding back to front, as people used to do back in the 80s, actually doesn't reduce boarding time any. You can board just randomly, and pretty much you get the exact same boarding time. And so they, ended up saying, well, that's fine. We'll just let people do open boarding, and then we'll charge them if they want to be the first 15 people on the plane or 30 people on the plane. So that's a way to monetize the boarding order and not actually affect your operations any. Of course, then other airlines figured that out, and so then they monetized it in even higher granularity, where you can pay extra to be in first class, and and a little bit, all these different boarding groups. And now, Southwest has given up on their open boarding, and so very soon they'll be going to a policy like much some of the other conventional airlines. And that all came from realizing that it actually doesn't matter how you board in terms of getting, on-time departures. But what's interesting is other aspects of how you board do make an effect on things. So if I go back to that susceptible, infectious, exposed, recovered, disease spread model, you can take a model that was like a system dynamics model, and you can then sort of implement it in a complex agent-based model system. So the same dynamics that are modeled by that SIR model, or in this case, SEI model, but it's very similar to an SIR model. And then you can study based on different boarding approaches, what's the likelihood that you're going to get more disease spread on the plane. And this is a group at ASU who did this a few years back. And they found that, without going into too much detail, that, they tested a bunch of different ways you could board a plane, and they have a probability of infection here. And they show that there's, a bunch of these don't really matter, but some of them do have a significantly different distribution of the newly infected passengers. So these three types here have a relatively low mean for newly infected passengers, but this one here, this triangular, this three section, as they call it, that boarding type tends to increase interactions between infectious people and susceptible people. And so, although it may not affect on-time departures, it could affect this other aspect, which might be, how disease spreads inside the cabin. So these are things that will be very difficult to study in a mathematical model, but you can augment a mathematical model with this fine scale agent-based model, and then start studying things that you didn't even think you could study back when it was just the simple SIR model. So that's basically ABM and ABM and SDM. So any questions about that basic overview? Okay. All right. So let's, I just want to then look at a quick pre-lab for NetLogo. And then if we have time, then do a post-mortem on lab 3, where you did the Monte Carlo, so we can understand the data that you got out of that. So let me flip back over to those. So we'll do. All right, so going into lab 4, ABM with the NetLogo, a lot of this is covered in the lab 4 video, but for those that don't want to watch the video or just want to get a head start on it, so quick intro to NetLogo. It's works on a bunch of platforms. It's Java-based, works on Linux, works on Mac, works on a Windows machine. You can download it for free. It was funded originally, I think, by NSF. So it's sort of a public good that's available, still being developed, still being maintained. It allows you to interact with the system as it's running, modify control parameters like sliding sliders around, display a bunch of variables, export data into formats you can then view in Excel or JUMP or SPSS or R, and then do complex experiments. So it can automate experiments so that you don't have to change a parameter, rerun, change a parameter, rerun. It'll do all of that for you. You can basically give it a schedule and say, I want you to try all of these parameters, basically the Latin square, experiment, the design for all of these parameters and all these parameters, or at least the full factorial design. And then it'll automatically go and do that for as many replications as you want, dump it out all to a CSV file. You basically let it run. It'll work in parallel across all the processors on your computer. You come back after lunch and your entire experiment is done. So it's a fun tool. It's a nice tool. This is so you can, it also has this web-based interface, which is kind of neat because they basically took all of NetLogo that ran in the Java app and they turned it into a JavaScript that actually runs inside a web browser. And so there are a couple of things like saving files that it can't do. But what's really nice is if you have a stakeholder or a collaborator that doesn't have NetLogo, you can basically put your model online and send them a link, and they can run your model inside a web browser without installing anything. And that it makes it very easy for you to say, well, to get a better idea of what I'm talking about, why don't you open up this link and set the parameters this way, and then they can play with the parameters themselves and watch how it changes the execution. So that's another nice thing. It's something that you couldn't, in Arena, you basically just can record a video and send them a video. Here, your stakeholders can actually interact with your sim via NetLogo Web, which is pretty cool. So this was an example I alluded to earlier, where these were some folks at ASU who were collaborating with NOAA, the National Oceanographic and Atmospheric Administration, to try to understand how best to alert residents of Florida when to evacuate when hurricanes are coming by. And so they took models that people understand of how people respond to social media, to TV, to radio, and so on. And they could test different strategies of alerting people through those at different timings. And they could test it then across multiple hurricanes, where they could see how people's experience in one hurricane changed their response at the next hurricane. So if you alerted them too early at one, it would maybe reduce their sensitivity to that information modality at the next. And then they could optimize over that, and they could study, do we get people out? And this was a GIS example where they took a real map of Florida with its highways and so on and so forth. And they didn't simulate every single resident of Florida, but they basically could create chunks of them and say, well, for every 1,000 people, they tried to model how that sort of parcel of people moved around. You could try to simulate every single resident of Florida, but then the question is, do you get anything by going to that extra scale? And so some of the challenge of ABM is figuring out how fine-grained is fine-grained enough, where if you get even more refined, would it change your results any? And they had to make those decisions. And so this is, again, an example of NetLogo combined with GIS, ABM GIS, which is popular. And so there we go. Then there are much simpler examples. So I could even open this one up on my computer here to sort of see it, but you'll have a chance to play with these things in lab. And I'd like to get to the lab 3 as well here. But this is an example that sort of says, how might pheromone trails work in ants that are foraging on multiple sites? And so they have simulated ants at the center of the sim. They have food sources that can be depleted throughout the rest of the sim. And the ants start searching randomly. And whenever they find a food source, they are programmed to have the behavior to come back to the nest and lay a chemical trail on the ground. And the simulated ground actually causes that chemical to evaporate over time. So you've got sliders where you can change the evaporation rate. You can change how much it diffuses to surrounding ground. And you can turn those on and off and study how those, plus the population, affect whether you get these strong trails that end up exploiting one food source at a time, or else you basically get no recruitment effect, and they all just effectively are just always searching randomly. So it's a way to study these simple parameters, diffusion rate and evaporation rate, and how it might affect recruitment. And in real ants that we see in different areas of the rainforest and so on and so forth, and in the desert, we do see major differences in their trail networks, in part due to what we think are differences in how chemicals that evaporate and are diffused and are laid down. So how much they lay down, how quickly they evaporate, and so on. So ants that live in the desert do not do trail. Ants that live in the really hot desert like the Sahara do not do trail laying because it evaporates too quickly. They have to use a totally different strategy for recruitment, if they do any recruitment at all. Ants that live in the rainforest can have very persistent trails because there's less worry about those trails drying out. And so you can play with those general principles inside a model like this. And then moving on there, so that's just pointing out that we have a lot of options when we run this thing. We can move sliders around, we can use buttons and so on. Then if we go further here, then we can design our own interfaces. So you can basically start with a blank canvas and then drop in, plots, inputs, sliders, switches, all of these different tools that then in the code, you can then say, I need a variable from the slider. Well, the slider just shows up as a variable. And so whatever they set that to, if you refer to that variable in the code, it will just take the value directly off the front panel. And so it's ways in which it's very easy to interact with the code. And then behavior space, this automated design of experiments. So once you have that front panel, you can go into behavior space, and you'll experiment with this in lab 4. And you can say, all right, I have a failure rate on my front panel. I want to try every failure rate from 0.05 to 1 in steps of 0.05. And it will just generate a long list of those. And for this particular model, this is a network model, I want to try the model with preferential attachment turned on, true, and off, false. And it will automatically do the full factorial design. It will take every one of those failure rates and every one of those preferential attachments, and it'll run each one of those combinations for 10 times. And then it'll dump that out into a spreadsheet, which then you can analyze later with your statistical tool of choice. So that's pretty nice. You don't have to manually update those failure rates and run those experiments yourself. So that's kind of neat. There are, in NetLogo, the entities are broken up into 3 types. There's turtles, those are the things that move around. There's patches, those are the ground that they move on, that don't move around, but they can have logic, whether, what color they are, whether there's state attributes on them. And then there are links, which are relationships between other agents. And so you can have 2 agents that share a link, and that might mean that whenever a variable gets updated on one, the link represents it's also going to update on the other one. Or that might just sort of create little batches where you can say, this is the parent of these 2 offspring, and I want to keep track of that network. Or it keeps track of history. Whenever 2 bump into each other, they form a link. And then later you can look at the networks that are formed over that. And maybe you get certain patterns where certain sets of individuals tend to attach to themselves and not the others, and you get segregation in your networks over time or something like that. So those are the 3 different types of entities that you can model in NetLogo, and each one of them can have different types of attributes. And so the turtle entities always have these by default. So you can always ask a turtle, what's your unique ID? It'll just be a number. You can give it a breed name. So this turtle, and by breed, this might mean this is a little bit like entity type, like this could be a call ahead patient, or this could be a walk-in patient. So the breed just gives you another way to differentiate among the moving agents in your sim. And then visual things, color, heading, where is it actually pointed in your sim? You can hide them. Sometimes it's actually useful to have agents that are moving around behind the scenes that the observer can't see, but you're making use of that agent. You can label them. You can update their coordinates so you can move them around. You can change their shape to be different. They could be like this kind of this is so the classic turtle shape, but they could look like ants, could look like cows. You can draw your own shapes, and then you can scale them up and down and so on. And then you can add whatever you want on top of that. So just like an arena, you can add attributes, and NetLogo, you can add attributes. Similar for the patches, they have a couple of built-in attributes, the patch color, the patch coordinates, the patch labels, but then you can add your own. So you could say whenever an agent crosses across this patch, it increases some counter that's on this patch. When the agent moves, the counter stays on the patch. So it's a way that you can kind of have spatially distributed information that provides another way that agents can kind of interact with each other indirectly, because 2 agents might visit this patch, but they don't visit the patch at the same time, but they might respond to changes in the variables that happened when the previous agent visited that patch. And then, likewise, you said you can have links, and then links have attributes as well. We don't use links a lot, at least in the types of things we do in this class, so I don't focus that much on links. But there are tons of examples that do use links, and you can find them in this wonderful models library. So under NetLogo, you get a models library. All of these are pre-built NetLogo models that have been categorized in a wide range of different application areas. And so there are full models like from earth science, from mathematics, from social science, and computer science, and so on. There are also things like code examples. There are curricular models. So like, if you want to demonstrate how an ideal gas works, there's a model of an ideal gas that you could be used in a classroom. So it's not quite used for research, but it's used for visualization or demonstration purposes. So this is a great way to learn about NetLogo, is to go through these examples. And in Lab 4, I'm going to basically have you pick 2 examples in particular from this list, and then run them, and then in one case, modify the others so that you can sort of get an idea of how these models work. So I'm not going to have you build a model from scratch. I'm going to have you start from a working model that comes out of this library. Now, to learn more about each model, once you load a well-written model, they all have an info tab. By default, the info tab doesn't have anything in there. Of course, it's not like they've, I guess in the future, they might integrate with ChatGPT and it could maybe look at the code and try to write this automatically. But it takes human effort, but all of those sample models, this has been well curated, and there's a nice description of how the models work. And so if you say like, oh, well, what is this ant colony model? What am I supposed to do? What does it show me? You can go into the info tab and read about it. And then you can go into the code tab and then see actually how it's implemented. And I think you'll see that very complex behaviors, when you run them, often have very short amounts of code that make that happen. And that's because you basically just have to specify a simple characterization of how each agent works, say how many agents you want, and then just say go. And it will then create a bunch of those agents, and it'll automatically have them interact and move according to your rules. And you didn't actually have to specify a lot of the ugly details to get them working. So you can get very complex sims running very fast in this platform. And so the way that, and you'll see this in the lab, the way that you get the code to interface with that front panel is you'll drill down into these elements and you'll say like, well, this button, go. Well, every time I hit that button, go, it's going to run a procedure in the code called go. And if I click this forever, then if I click down the go, it stays down. And so it just keeps running go over and over again until you click it again to pop that button back up. And that's how you get continuous runs of the sim. So if you turn that off, you can step through the sim step by step by step. You turn it on, then it'll just let the thing run. And so usually in these sims, you might have a step button that allows you to debug and just go through step by step. But once you're kind of comfortable with it, you hit go and it just goes. But that's what you drill down into these buttons, and that is sort of what then communicates with that code. So this is what a go button might look like. So this might be what runs every iteration through. So every time that go runs, it asks every turtle that's been built if its ID is greater than the current time. And if it does, it just stops. And in this case, that will make it so that the turtles gradually trickle into existence. Turtle 1 will be the only one that this isn't the case for, so that it will pass through here. And then when time 2 comes on, then turtle 1 and 2 will allow to go through here. Then time 3, 1, 2, and 3. So this is just sort of a trick that allows you to sort of, rather than having all of the turtles be unleashed at once, it allows them to sort of follow the clock. But then after that, there's sort of very simple logic. So is my current color red? If it is, then run a routine called look for food. If it's not, return to nest. Well, this shows you that you can change your own color. So by changing your color, this will change what you do every time that go happens. So maybe in look for food, once you find food, you'll change your color to red, indicating you currently have food. Well, then the next time the go runs, you won't look for food, you'll run the return to nest. So it's kind of how that runs. And this ask is basically going to say, like, that's sort of like for I in 1 to number of turtles, but it's doing that all behind the scenes. So this simultaneously, whenever you ask a group, you can just count on all of those groups, all of them doing this simultaneously. And you don't care how it's actually being done. NetLogo will just make it happen. So they'll kind of, this will sort of set their direction, and then they'll randomly perturb that direction to make it look more realistic, and then they'll move forward FD by 1. And then after that, these ants that we're simulating here will they'll ask the patches to diffuse their chemical out to the rest of the area around them and then evaporate that chemical as well. And so that's it. That's basically all of the sim there. So there was a little bit of setup that I'm not showing here that created all the ants and created all the patches. But after that, the actual sim was this relatively short code that, and I haven't shown you what look for food does or return to nest does, but that, I mean, this is just going to set a heading direction because this is where the movement happens. So it's really easy to get very complex sims running out of the box in this program in NetLogo. So you'll see more of this. There's some things that are a little bit weird about NetLogo that I hinted at there, that agents have to be asked to do things. So you don't think about a vector of agents that you have to go through and run the movement command on. You just say, ask all of the agents to do something. And so that's something that's a little bit different. You are yourself a sort of godlike agent called the observer. And so there are ways in which from the NetLogo panel, you as the observer can issue new ask commands while the simulation is running. So you can pause the sim and then ask all of the agents to re-randomize their positions and then go again. So you can sort of inject code as the observer while things are running and then get values of those agents while things are running as well. Each agent as it's running can modify itself, its own parameters, but it also can ask others. Like if you bump into another turtle, you can say, ask all of the turtles within 1 unit of me to update their color to blue. And if you do that, then it's like an infection and color is spreading so that whenever one agent bumps into a bunch of others, as long as they're close enough, they all turn blue. And you could watch blue spread through a population that way. And then you can also just ask them for information. Ask all agents around me to tell me, ask for the average of the age of all agents around me. And you'll get that information, then you can use that in logic. So there's sort of these things that agents can do between each other. Agents can also modify the attributes of the patches. They sort of temporarily absorb the attributes of the patches they're on. Once they move away, they lose access to that patch. So this is sort of the basics of the programming paradigm. For more help, and again, you'll have more opportunity for this in Lab 4, but this help menu in NetLogos, not only do you have the models library, but it's got a dictionary, which basically allows you to look up every single command in NetLogo and get a brief description of it. This user manual and the users group. The user manual here, this kind of giant programming guide, has got it's a whole tutorials on models, commands, and procedures. It's got reference here on the way you use different things. It's got additional features like how to use behavior space. Like it's a really well documented program. It's really well done. I think it's much better done than a lot of commercial programs in simulation. It looks a little cartoony. The visualization is maybe not as nice, but what you're paying a company like Rockwell for are the sort of fancy 3D visualizations, but the interface is awful, and I think you'll see that. But here, I think the interface, once you get a little bit used to it, is pretty nice, but they don't have the flashy visualization. So that's kind of the trade-off here. So yeah, this is just kind of showing this is what the dictionary looks like. What does any question mark look like? You can right click on it, say go to the dictionary, it'll pop it up, and then it'll give you a description. It will then give you see also, it'll give you examples and so on. So very easy to learn NetLogo. Likewise, grammar and syntax. It has these whole, like if you go in to look up breed, it'll show you these little examples of how to use breed and in these different ways. And again, a lot of this documentation, it's really great. It's a fantastic program. It's easy to use. Again, it just, the visualization is not always that great or not that awesome. Code examples. So you want to, how do I draw a box? How do I create a ball that bounces around a room? They have a bunch of these pre-built examples, a whole set of examples on integrating with GIS. All of them, you just open that up, take a look at the example, take a look at the code. You can copy the code out, build your own examples around it, and so on. And and then this is kind of an example of a model that they have that simulates tree growth with water and sunlight availability. And so, it creates these different breeds of agents. So there are leaves, there are dead leaves, there are raindrops, and there's the sun. It creates the attributes that the different agents own. So the leaves have these attributes that only leaves have. The raindrops have these attributes that only raindrops have. And then there are global state variables that everybody has access to. And then so that's how you would start one of these simulations. And then you can ask the simulation to sort of instantiate all the patches with different colors. You can create a certain number of leaves. You can ask the leaves to do their business. And what you end up getting out of that is, I guess I'll just open up NetLogo and that model in particular, because this is kind of a cool model. This particular model. And what you get out, so opening up NetLogo here, I'm just going to go into the models library. This one, I'm going to search here for this model. I forget what they call this model. I think tree, I think it's called autumn. Yeah, I think this one is the one that's, so then this particular model, then this is what it looks like when you first open it up. And so if I hit setup, it creates these leaves and so on. And if I were to hit, so it's got the sun, it's got the leaves, it's got temperature, rain intensity, and so on that I can update. And then if I were to hit go, then it actually simulates the processes that we think of are responsible for deciduous, basically for leaves that fall. So you notice these leaves all change their color and then they fell. That wasn't just a kinematic model based on timing. That was actually based on processes that are modeled as how we think leaves work based on the availability of things like water, the temperature, the surrounding humidity, and so on. And this is a good way to then show how those things work as the kind of things move towards fall conditions. And so if you change some of these parameters, like how intense the sun is, what the temperature is, how little rain is or whatever, then you can get different patterns for how quickly the leaves fall, what color they are when they fall, and so on and so forth. And so this is kind of, maybe not what you think of as a traditional agent-based model, but here I think this is cool because they're actually making like leaves, the sun, each raindrop, those are the agents that are moving around in the system and interacting with each other. And that's what's giving you this complex emergent behavior that's coming out of this. And so I think it's kind of a neat model, maybe not, the not directly related to IE for sure, but I think shows you the types of things that you can do. And so, and I don't want to go into too much more detail on this particular model because you'll get examples of this in the lab. But and I won't do this now, but this, again, just showing you how simple these things. This is an entire NetLogo program that if you were to copy and paste this off the slide tab or off the slides into NetLogo and run it, you would get a complex behavior of turtles that move around randomly and interact with each other and get some emergent patterns that come out of it. And that's in, I don't know, 20 lines of code, the entire program that does what I think if you were to try this, it's kind of impressive what comes out of these things. So it's it's a powerful tool. Again, the visualizations look a little childish, but I think it's a very useful. It's shown that it's been a very powerful tool for people in research. So we'll be doing segregation and fire in lab 4. I'd also encourage you, if while you're in there, to take a look at things like the traffic grid and Hotelling's law. These are also some nice models that have some concepts that I think are relevant to applications that we might be interested in. But then there's also a huge NetLogo user community and modeling commons where people have done things like supply chain modeling, the financial market, certainly the beer model that folks use in other classes has been implemented in NetLogo. So a huge contributed community of models as well as the ones that are built into the samples. So that's NetLogo. Again, you'll get more introduction to it in Lab 4, but any general questions before you go into Lab 4 and kind of unleashed on your own? Okay. All right. So I wanted to make sure that I cover a little bit of the Lab 3 interpretation, because these are a little bit more traditional results from in industrial engineering. So in Lab 3, we're experimenting with Monte Carlo simulation. And so one example application of these numerical methods is experimentally determining pi by stochastic simulation. So normally we think about pi, you think, well, how am I going to approximate pi? Maybe I have to use a Taylor series expansion, or there's all these different kind of ways that are kind of informed by geometry, but they're very analytical. And in this case, you can basically throw darts at a dartboard and approximate pi. And the basic idea here is if you were to throw darts at a dartboard, some of the darts would land outside the dartboard, some would land in. And if you threw enough of them, then you know the area of the square around it. And so the fraction of those that land inside the circle relative to the square, well, you know that the area of the circle is pi r squared. Well, the area of the square is 4r squared, right? Like if r is here, then it's 2r on one leg, 2r on the other leg. So the square is 4r squared. The circle is pi r squared. The probability you hit the circle is just pi r squared divided by 4r squared. So the r squareds cancel. And that probability that you end up getting is pi over 4. So if you throw enough points at this shape here, and then you just calculate the ratio in the circle versus out of the circle, that's going to converge to the probability pi over 4. So if you just multiply that thing by 4, you're going to get an approximation of pi. That's basically the gist of what we do here. So the probability that you land a dart inside the circle is just pi over 4. And then so if I just simplify and focus on just this corner here, just this upper quadrant, I get the same thing. So what's the area of this upper quadrant? Well, that's just r squared. What's the area of this sector here? Well, that's just pi r squared over 4. So again, the probability that I hit the green area over the total area is pi over 4. So if I throw a bunch of points at this and gradually build up a proportion of points in versus total, then that will gradually converge to pi over 4. Multiply by 4, I got pi. And that's basically what we can do. And so you can generate a bunch of random numbers between 0 and 1, another bunch of random numbers between 0 and 1, call this x, call this y, and then we can, and that's basically throwing a dart at a dartboard. And then we can say, did that dart land inside the circle or not? Well, that's just, is x squared plus y squared less than or equal to 1? If it is, it's inside the circle. If it isn't, it's out. And so that turns us into a group of ones or zeros. And then we just see what is the average number here. What is the fraction of rows for which we got a 1? And that is what that count divided by total, you multiply by 4, which is how I do it in Excel, gives me an approximation of pi. So that's one of the examples of how we can use stochastic simulation to make these approximations just by, generating random numbers and asking which random numbers, when did random numbers meet certain conditions. So were there any questions about this basic idea of why this works, why generating thousands of numbers between 0 and 1 allows us to calculate pi to arbitrary precision? That makes sense. You're just estimating a proportion of points, and that's where the stochasticity comes into play, because this ratio will converge to the probability. Okay, so that's the kind of the simple example of this. Now that allows us to sort of talk more about outputs of stochastic simulation. And so if I run this for 500 rows, 1,000 rows, 10,000 rows, 100,000 rows, or 1,000,000 rows, then I can generate not only an average, which is the sum of the ones divided by the number of rows, but also a standard error of the mean, which is basically that the standard error of the mean is not the standard error of the ones and zeros. It is the standard error that we would expect if I were to run multiple experiments with 500 rows. So that term, standard error of the mean, it ends up being the standard error divided by square root of the number of rows. But what that's modeling, and this is something we'll talk about later in the semester, why this is the case, is if you were to run this experiment over and over again, then we would expect the mean would come out of a distribution that would have this standard deviation. So I run the experiment once, it's here, once it's here, once it's here, and so on and so forth. If I were to put that into a distribution, then this would be the standard deviation of that distribution. So we can sort of plot it anchored at our current estimate of the mean, and that kind of gives us a rough estimate of where we think other means might be. And so I see that if I increase my number of rows, my number of Monte Carlo trials, I get different means. That's just because I reran the sim, I'm going to get different means. But my confidence gets tighter and tighter. So this is the reason why we run multiple iterations, is that we want to collapse the estimate onto and around a point. And we can make that a little bit more useful by using these things called confidence intervals. So a confidence interval is a version of the standard error of the mean that gets scaled by a critical t-value in a t-test, so that this range represents all hypotheses that you cannot reject with these data. So basically, if you were to test 3 against these data, a t-test would say t less than 0.05, there's no way 3, there's no way this distribution came from a distribution with a mean of 3. So I would reject 3, but I could not reject 3.05 for this distribution. The p would be greater than 0.05. So all of those numbers there are ones that I cannot reject with a t-test. So they might be the real mean. And so notice that as I increase the number of Monte Carlo trials, it collapses. The other thing I want you to notice is that 3.14, the actual value of pi, is in every confidence interval. And that's what we would expect, because in this case, we pretend like we don't know the real mean, where we hope that 95% of the time, the real mean will be in any confidence interval. So that's basically what a 95% confidence interval means, is that if you generate one of them, then there's only a 5% chance it doesn't include the real means. So if I were to keep doing this over and over and over again, eventually I would get a confidence interval that doesn't include 3.14. But 95% of the time, every time I generate a confidence interval, it will include 3.14. And that's the reason why all of these confidence intervals happen to include 3.14, and they all collapse around it. So that's what we do with confidence intervals, and that's why we're going to use confidence intervals to use as our outputs of our sims. And this will become really important as we look to the back end of the course after the midterm, is then using confidence intervals as interval estimates from our stochastic sims. We don't ever want to report points. We always want to report intervals. Okay, so any questions about what I mean by confidence interval here? We'll get more of this, again, the back half after the midterm, but I at least want you to sort of get the idea here that every time you run your Monte Carlo sim, you're going to get a different point estimate. But 95% of the time, the confidence interval will include the real population mean. And that's why if we increase the number of rows, we tighten our confidence intervals so that we have more confidence that, well, I have no idea if pi is, I know that pi can't be 3.2 or 3.1 if I've run 1,000,000 of these. So I can't tell where it is inside this little green bar, but that's pretty darn close. That's probably close enough for my application. Okay. Other things I wanted you to pick up into this is the generate random numbers in Excel. You use this rand function, so it draws a random number uniformly between 0 and 1. We're going to see that a lot, especially going into the next unit. And then these activities here. So I'm not, I mentioned this, I hinted at this before, but the big thing I wanted you to take from this is that if you look at the distribution of these activities here, that the duration ends up being this weird asymmetric thing. So this is of the total network, where you get sort of a heavy tail of activities that end in a relatively short amount of time, and then kind of a big clump of them that end over here. So there's, if you look down then at which path ends up taking the longest in that activity network, it's very often the one that has a single value or a single activity. And if you think about it, that should make a lot of sense, because even though all of these activities have the same mean, the three-part activity, in order for you to hit 12 minutes in the three-part activity, you have to independently hit 4 minutes in all of these activities. But these activities are unrelated to each other. So if you get 4 minutes here, it's unlikely you're going to also get 4 minutes here and 4 minutes here. And that's why the central limit theorem works. That's why in the central limit theorem, as you keep adding independent variables, it becomes more bell-shaped. Because what independence does is it decouples outcomes, so that even though the means are the same here, it becomes unlikely that you get the extremes, and that pulls down the edges on the extremes, which is why when you sum independent variables, it gets more and more bell-shaped, because the extremes become less and less likely. And that's the other thing I wanted you to take from that. So that's kind of the biggest thing. I don't really need to harp too much more on this distribution here. The big thing of Lab 3 is I just want you to have experience doing these Monte Carlo simulations. So let me get to an iClicker for today, and then I'll let you go. So we'll talk about that. All right, so the iClicker for today is, what are the moving agents, and I'll start that, sorry. What are the moving agents inside NetLogo called? So I said there's 3 types of agents: ones that model the ground, one that model relationships, and ones that actually move. And so what are the moving ones called? Okay. If I can manage to get Duo to let me into iClicker. All right, poll. All right, there it goes. What are the moving agents inside NetLogo called? One word. There are 3 types of agents. One of them moves, one of them stays stationary, one of them is about relationships. What are the moving ones called in NetLogo? And that's all I've got for you. So then we'll see you on Thursday as we move toward drawing random numbers and random variate. Uh-huh. No, that's all right.